ready. Let your mind work out.
Good evening, ladies and gentlemen, and welcome to Asvab Weekly. This is Kieno Thomas. The next thing, or the next mechanical comprehension essential concept that I'd like to introduce you to is in the area of weight and balance. Okay, so first off, we have some terms that, or not necessarily terms, but just some like points that we use in the area of physics. We have something called a vector. All right, and a vector is just, it represents a force, like kind of like say like when I used to flight instruct, and you know you have an airplane flying through the sky, and it's got the engines hanging and it's just buzzing through the sky, but you have the force of lift, weight, lift, weight, this is lift, this is weight or gravity, this is thrust, and this rearward force is drag. Okay, so just to get you to understand, when you have, now this plane is considered to be in what we would call level flight, so you have a vector or an arrow representing a vector, which represents a force going upward, and you have one going downward. So these two forces kind of cancel each other out, and these two forces kind of cancel each other out, the thrust and the drag. So this is unaccelerated level flight. So I want you to get the concept of just forces actually zeroing each other out, or counterbalancing each other, if you would. So now back to how it applies to us, the vectors, not so much the airplane, is what I'd like you to focus on. So now in this segment, I'd like to go back to the class of lever. Okay, the first class lever was the seesaw concept. So we had the fulcrum in the middle, or pivot point, right? Then we had a plank, right? And then the way we made it look is like we had one vector representing force or effort that we had to apply, and then on this end, let's say that's just a bowling ball, all right, we have a load that is kind of going with gravity. So in order to keep this thing balanced, both of these forces are kind of counterbalancing each other, going downward. So, a couple concepts that I would like to introduce you to. Something called a load moment. A load, L-O-A-D, and a moment, M-O-M-E-N-T, a load moment. And the load moment, for our purposes, are going to be in what we call pounds, inches, and I'll explain that in a minute here. In pounds, inches, and I'm just trying to make sure we are getting the real estate from our trusty camera here. All right, so load moment in pounds, inches. The load moment is a combination of, let's say this is a reference point, or what we would call a reference datum line. And you don't necessarily have to remember that. All you need to know is that we're measuring things from this fulcrum, all right, or the pivot point. So in order for this thing to balance out perfectly, they would have to be the same amount of distance. Let's just say we say this is 10 feet or 120 inches. I like that better. 10 feet is 120 inches. And let's say that this bowling ball is 10 pounds, all right, then what we would say is the load moment is a combination of the distance and the pounds from the load moment. So it would be, what do we have? 120 inches, 10 pounds, 1,200 pound inches. Okay, so this would be 1,200 pound inches. And in order for this to perfectly balance out, this would have to be 120 inches. And the force that we exert is going to have to be, 10 pounds. I don't know why I wouldn't put 50, but 10 pounds. So here, if we have 120 pounds, 10 pounds of effort, then we also have 1,200 pound inches load moment. And just think load to pounds, moment, inches, distance from the reference datum. And honestly, what you could look at this is like an equation. The fulcrum, just think of that as the equal sign. And you have to think to yourself, does 120 inches times 10 pounds equal 120 inches times 10 pounds? And if the answer is yes, then you have a perfectly balanced equation. Now, this is what we call the first class or class 1 lever situation. All right. And we'll continue in a moment. Okay, so that was pretty cool. And I just thought about this equal sign and things balancing out. So it's always nice when you can think of new ways to kind of bring out information. Now, a second type situation would be, and remember our vectors now, and our class 1 lever, we had two forces reacting downward. Okay. Now, that's the first class lever. And I'd like to talk about trying to pick out a really good situation here, because I have a bunch of questions in front of me here. And I want to give you the best ones. All right, so let's say we have a fulcrum here. And we have trying to get this thing to focus. There she goes. All right. Okay, so we have our fulcrum here. I'll label it fulcrum. Okay. We have an upward force, an upward vector, and then we have a load, a downward vector. All right. And 60 pounds is what the downward vector is exerting. And the 60 pounds is approximately 14 inches away. And then this distance from the fulcrum is 4 inches away. Okay. So now what the question is asking, what is the force required to balance out this weight? Okay. Now, our given is we have a load moment that is existing here, right? And that will be 60 times 14, and it would give us a result in pound inches for a load moment. Okay. Just pull back, get a little bit more real estate there. Okay, so what I would do is I'd say 14 times 6, 24, 84, 840. I multiply by 6 and then add the 0 later. So 840 pound inches. All right, now in order to see and I'll put this right here, 840 pound inches. In order to see what balances out with that, the only thing that you would have to do is the weight that you're going to exert upwards to balance out with this. I'm going to divide 840 by 4, and just looking at it, 210 pounds. What you would do is you would divided by 840, and right off I could just look at it and see it was 210 pounds. So in order for this to balance out, this force upwards would have to be 210 pounds, and then 210, I'm sorry, that was 210 times 4 is 840 pound inches. So we have 840 pound inches here and 840 pound inches here, and that is what is required to balance it out. You could have another type of question where you would have them give you an upward force and then a fulcrum down there, and they'll say this is 10 feet, and let's see, got a 2 feet measurement, and they would want to know what is the mechanical advantage if we apply our force here. What is the mechanical advantage of this machine? All right, because it's a lever, it's a machine. We add force to it and we multiply our forces added to it. So what you would have to do is you would have to take the distance, the effort distance, and divide that by the, what do they call that? Load, okay. Effort distance divided by load distance, which will be 10 over 2, and the mechanical advantage of that would be 5. So that is another sample mechanical question. Another thing they may do, and I want to be real careful about how to handle this, you'll have a sailor or a soldier bending his knees, and he's got a wheelbarrow, right? And the wheelbarrow gravitational pull is exerting in that direction, and from this point to this point is, say, 2 inches. Okay, and let's say the load is 300 pounds. All right, so remember, this is the fulcrum, this is the reference point here, that is the fulcrum. So everything's being measured 2 and 3, so we will be exerting 600 pound inches. All right, and let's just say the distance from where we're actually lifting, where we have our hands on the wheelbarrow, is, let's just say, 8 feet. All right, so at this point we have 600 pound inches being pulled down by gravity, and our machine is actually going to help us out, to help us carry this load. So we have 8 feet, and if we take the 600 pound inches and we divide that by 8 feet, 600, 756, 40, 75. So 75 pounds of upward effort is what we're going to have to apply, and that's pretty good. We got 600 pound inches being exerted, a 300 pound weight, and if all we got to do is apply 75 pounds of force in order to get this thing up and rolling, off the little, you know how they got the little feet on the bottom of the wheelbarrow under the handle. They got the feet. So that's all I got to do is get that up to 75 to move 300. I say that is a pretty effective machine. All right. And we could even, at this point, calculate the mechanical advantage. Might as well play with that too, right? Our mechanical advantage is our effort arm over load arm. And the arm is the distance from the reference point. It's our fulcrum, it's the distance. So our load arm is 2 inches, and our effort arm, we'll say, this was actually 8 inches. Sorry about that, not feet. 8 inches. So we have a mechanical advantage of 4, which is pretty good. And this is the multiplier of the force applied. So the machine exerts a certain force. It's like a multiplier almost. And 75 pounds, mechanical advantage of 4 equals 300 pounds. See how that works? So again, I know that was a lot, but just, you know, slow it down and, you know, try it out. Another type of question they could give you, they'll have like a pulley system, right? Let's say this is blocked and you got a pulley coming down and you got a bottom pulley like that, right? And let's just say where your line comes in, let's say there's just boom, that's what you're actually pulling, and then bang, and then it goes around the reel. Okay, so we don't count this line, right? We count these 2 lines, and this has a mechanical advantage of 2. Okay, so you never count the pull line, you always count that line. Now let's say we had a situation where we had a big pulley, and then we had 2 little ones, right? So then the system would look like this: 1, 2, 3, 4. Okay, so then we got a line here, we got a line here, and we got a line here. So the mechanical advantage of this pulley system would be 3. We never ever count the pull line. We only count the lines in the loop. Okay. Alright, so you know what? That's where I'm going to keep it right now. Just to recap, we talked about our class 1 lever. When we have 2 forces, in order for them to be balanced out, we have to have the same distance. Only for the class 1 lever, the same distance from the reference point, which is the fulcrum or pivot point. And we want the same amount of weights here. Oh, you know what? I'm glad I even did that. All right, check this out. What if we had our fulcrum and then bang, right? We had, think of it, and I hate saying this, but hey, it's true. We all saw it when we were kids, the fat kid and the little kid. Let's say the little kid is 50 pounds. He's 50 pounds. It's like the little brother. All right, we'll say little brother. We won't say fat kid, little kid. We say big brother, little brother. So the little brother's 50 pounds, and he is 100 inches from here. 100 inches, right? 50 pounds. Then his load moment would be exerting 5,000 pound inches. Okay? And let's say this dude was, let's say 20 inches. The big brother is only 20 inches from the reference point. How heavy would this guy have to be to keep this balanced? Well, again, we have 5,000 pound inches, and if this guy's only going to be 20 inches, if I can hold on to my marker or my dry erase, then I would take 5,000. I will multiply by the 20 inches. And 2, 40, 1, 0, 0, 5. So this guy has got to be 250 pounds. And in the class 1 lever system, think of this as an equal sign. Okay? This guy is 250 pounds times 20 inches and 5,000 pound inches. This guy on this side is 100 inches times 50 pounds, 5,000 pound inches. So 5,000 pound inches equals 5,000 pound inches. All right, so you see how that works? So if I come up with any other funky ones, I will definitely let you know. But normally, typically, in order to be perfectly balanced, the same distance and the same weights, if the fulcrum or balance point shifts, then you see this guy has a shorter distance, so he has to exert more weight in order to be balanced. So literally, there's a 250 pound kid here, a 50 pound kid here. This guy is 4-5 times. So, and that even gives me my mechanical advantage. The mechanical advantage is effort arm over load arm. Okay, if I want to calculate the mechanical advantage of this system, and they do have questions where they're going to like, so it's effort arm, which is just the distance, that's what we call an arm, over load arm. Okay, so our effort arm is 100 inches. The load arm, because this guy is trying to balance with this guy, he's way heavier. So the lighter guy has got to be like, yo man, I'm putting in the effort, this guy's the load, he's the heavy load, like, oh man. So, and this guy is just 20 inches. So we reduce, I'll chop the zeros off, and then reduce 5. That is my mechanical advantage. 5 of this system. That is the mechanical advantage of the system. Alright, so I'm looking where I'm at on time. I didn't want this video to be too long. I'm going to leave you guys with that. But that is just the second mechanical advantage, the mechanical comprehension concept that I wanted to leave you guys with. If you guys have any questions, you don't understand something, all you guys got to do is leave a question mark or tell me what you'd like me to explain further in the comment section, or even if I need to break it down more. Thank you for watching the Asvab Weekly Mechanical Advantage. I'm Kieno Thomas. Have a great evening.